Basically, the rule of thumb is like if you don't have a lot of data, you can try machine learning, like traditional machine learning. If you have a lot of data, it only makes sense to use deep learning. This has changed a little bit because now we have pre-trained models on so many different kind of base domains, like for example, vision. And even with a little bit of data, you can already fine-tune what's called fine-tune the vision model to be good at the specific tasks that you want to give it. And with language, that is now even more true than ever because we have these crazy language models that know so much about language and about so many things in the world. And by fine-tuning them on specific tasks with very little data, that would be basically impossible. And even machine learning models couldn't do it at that point. You can get really good results. I do think that deep learning is slowly but surely making everything else in machine learning irrelevant. Slowly but surely, I think.
I've been spending a lot of time on Twitter, which is probably not the best thing you can do, but seeing what people are building with AI, and basically what I'm seeing is everyone is building a service layer or an application on top of a large language model, in general GPT. I don't know if that's the way the future should go, or if we need more actual AI engineers who know the models, who can build models from scratch, who can train them, who know the right architecture. And for that, for sure, you need fast AI. But if you are just a software engineer that wants to build applications leveraging AI, maybe you don't need that. But maybe we can discuss that later.
Yeah, let's discuss that later for sure.
Yeah, so I wanted to start, as you saw, I sent you a couple of notes before, with your background. Because you didn't study computer science, if I'm not mistaken, right?
Exactly.
You got into it self-taught.
Yeah.
How was your journey with that?
It was an interrupted journey. So I started kind of quite young with I liked computers, like, a lot of kids, you just like computers. And I learned BASIC. Basically, an uncle of mine taught me BASIC, and that's all I knew. And I was like, okay, this is pretty cool. You can make a calculator with it. That's as deep as I got with BASIC. And then I met my friend Jurep Jauma, who is this kid who is super also into computers as well. And from there, basically, we bonded because we both knew BASIC. Basically, that was the thing. And then from there, I started learning some C because I wanted to make games. I think that's a typical story for many kids. So you want to make games because you play games and that's what you are interested in. So I learned some C. And I got really disappointed with the experience. So it was really hard. And it was impossible to get anything working, at least for me. So I felt very frustrated with the experience. I was like, I'm not making any of the games that I play, like this is useless. So basically I got tired, jaded from programming at age 12, I think, and I left. I stopped.
The fastest burnout ever.
Yes. And my friend Jama actually kept programming JavaScript and HTML and all this stuff, and I didn't see the point of any of it. I was like, I just want to make games, and I cannot make games. So this is stupid, and I hate it. That's it. that shows my patience back then, which hasn't changed that much.
We can talk about that maybe. But what kind of games were you trying to do? Like, just to understand.
Right. Like, for example, at that point, I was really into point and click games. Lucasfilms, adventures and things like that. And those were amazing. But it's really hard to make anything even close to that. Even platformer games. I mean, you need to learn, SDL and all these things that basically you need to learn low-level programming. And for me, pointers were a really huge problem to learn. Like at that point, I was like, I don't get it. I don't get this. And yeah, so that discouraged me a lot. And then HTML for me, it was kind of cool, but I didn't see the point of JavaScript. That's quite funny. I thought JavaScript was useless, and no one ever needed JavaScript for anything. And
But when was that? Just to know years, more or less. Was that?
That must have been 97.
I mean, 97. It's not even Web 2.0, so no that much interaction in the web. So yeah, maybe I can understand your thinking process behind that.
It was a new thing basically that I thought was pointless, because if you have links and marquee and all this stuff that you had in the web 1.0, why would you need JavaScript? I never saw the point. And then, I got bored with that, and I went on and ended up studying political science, actually. But I never finished because towards the end, I was doing a part-time job at a bank, kind of a support job, customer support. and I got really jaded, and I quit the job after 2 years, and I was like, okay, I don't know what to do. And that was at the point where Jaume actually kind of contacted me and told me, hey, you should come back to program again. And I wasn't really sold on it, but I'm so glad he did, because thanks to that call, basically, which was a very long call about Ajax and client server architecture and lots of things that I had no idea what he was talking about, but he was super excited about it. So I got back into it and started learning databases and JavaScript. And I was super lucky to get a job right away with him, and in a small team of a web development agency. And that was great, because then that allowed me to learn on the job 8 hours a day and get paid for it, which is an amazing experience for anyone who's basically been hired as a junior. That is an amazing experience. You learn so fast, and also they pay you for it, so it's amazing. And from that point on, I was in love. Like, I was like, Jesus, I've never even thought that you could love going to work. And I was really hooked, completely hooked to programming at that point.
I mean, there are so many things here. First, I want to get deeper into the political science topic, like you studying that, like, why, how, like from your passion programming, then getting basically done with C and then going to political science. But I wanted to mention that it's true that in software, I've seen quite a lot this thing of being a junior and being paid for learning. I think because it's still a growing industry and there's more need of talent than there's talent available. I think that happened to a lot of people. Like, basically you get paid to learn, and that's an amazing opportunity. And even at leadership roles, like, there are not enough leaders in the market, and you get paid basically to learn the job. So yeah, I think that's amazing. But going back, like, how do you get interested in political
Why
science?
political science?
Yeah.
I don't know. I was kind of into history, and I liked, literature and all this stuff. So in school, basically, at least in Spain, they kind of guide you towards a path that is either science and math, or like humanities and language and all this stuff. And I did like math, but obviously I wanted to kind of get deeper into history and language and so on. So basically, I ended up going the other way, like the non-science and math way. And then, because I was reading history books and stuff, I had some friends that were a bit older, and they were studying political science, and they were, having all these crazy conversations and like talking about history and stuff. And I was, wow, that's really cool. I just want to do that. That sounds really fun. So I started doing that, and it was quite fun, to be honest. But then, when I started programming again, and like, in this job and stuff, I quit, because I was like, oh my God, I mean, programming is so much more rewarding than any of these things that I'm doing. Basically, in political science, I felt anything you learn is it basically doesn't equip you to solve any problems. Basically, you only learn about problems that you cannot solve, and you can never solve, and no one can ever solve. So that's really discouraging, actually. At least I felt that it makes you quite depressed, as a student. You learn about all these problems and the wars and all this stuff, and then when you program, you're basically solving problems all the time, and it's super satisfying.
Do you think AI can help us solve these problems in political science that you are mentioning that are not solvable?
I'm not sure, actually. I'm not sure. I tend towards no, because these are problems that are with our nature, in a way, or like the essence of these problems are basically have to do with our nature.
Mhm.
Some of them have to do with limited resources, of course, and that maybe the AI can help with that. And I think that could help a lot if we can make some of the resources unlimited. But yeah, there's something deep in our nature that we'll have to deal with or without AI, I think, at some point.
So basically, the root of all problems that you study in political science is human nature. And for that, you probably need to tackle that more with psychology, philosophy, and even religion, if you will, not
Yeah,
AI.
yeah, and even then, I don't see a clear path. Maybe it's because I consider myself an optimist, but when I was studying political science, I was not an optimist, for sure. I think I've changed my personality thanks to programming. Maybe that's possible.
So, talking about programming, not only the application of it, but also thinking about the problems. What I know from you is that you are very good at thinking in abstractions. Like, hey, this is the specific problem, but when I'm looking at this problem, I'm also looking at the range of problems that are above that and that we can think about as well to solve this problem in a way that will solve the future problems that are at least related. So, is there any specific way that you tackle, or any framing or way of thinking that helps you when you see a problem and you think about the abstractions? Or how do you even tackle that?
I think this is basically something about the way I think about problems that is heavily influenced by having learned functional programming early on. So this is something that I've seen diverge with me and some of my colleagues, which is that I got really into functional programming, which is this kind of trend in programming that's almost like a cult, you would say. But it's really, really amazing. Like the way of thinking is completely different from what I think they teach you at university currently, or at least back then when you study computer science, which is a much more kind of imperative, kind of traditional way of programming. So thanks to functional programming, if you go really deep into the rabbit hole, there's basically, you touch category theory. And at that point, basically, you're always encouraged to look for the abstraction and the general rule and the more general case and the more general case. And it can be pathological in a way, but I think this is a kind of bias that I have. So when I look at a problem, I try to not consider it a single instance of a thing, but rather, hey, let's think of this as a, for example, a compiler problem. This is another thing that influenced me a lot. I got really into compilers and programming languages and kind of writing your own programming languages and toying with that. And that basically made me see everything as a language that you need to parse and compile and then interpret or something like that, you know? And that's something that surprises some of my colleagues sometimes, because it's not obvious to them that, you know, this is a way to see the problem, but it's my bias. Of course, there's other biases. And I think the key here is having more and more kind of tools in your toolbox to frame the problem in different ways. I've been known to sometimes kind of, you know, use the hammer for every nail, you know, because it's the way I see the problem. And then someone else comes along and says, no, actually, this is more naturally expressed in graphs, for example. I know some people that are obsessed with graphs and they say everything is a graph. And, you know, I'm not one of those, but I understand, you know, maybe they see something I don't see, you know. So I think it's worth learning about all these things and kind of trying to always challenge the way you see the world so that you can have a different perspective.
Can you tell me more about
Category theory?
categorization theory? Yeah.
So this is, as I understand, it's a kind of math, basically a branch of math that looked at things, for example, like addition, like, you know, things that can be added together, right? And you can, in programming, for example, you can think of numbers as, you know, you can add two numbers together and you get a number back, right? And then there's other things that you can derive from that. For example, if you add 0 to any number, you get the same number back, right? So these kind of laws that also you can add in any order and you get the same number back and so on. So these kind of things, basically, in this case, they're called monoids, right? And then you can start thinking about things that behave the same way, but that are not numbers. And this is where it gets kind of interesting. You can think of strings as monoids as well, because you can add them together, concatenate them. In this case, order matters with concatenation of strings. So maybe in category theory, there's a special case that is not exactly a monoid. I don't remember any of that stuff anymore, but yeah. So then basically at some point, you interpret, you're talking about very high level domain concepts, right? Like imagine that you have like user accounts and like things like that. And then a category theorist would immediately see, okay, the user accounts are monoids because you can merge them together and then you get another user account back. And it doesn't, you know, something like that. And everyone goes like, what? Like, what is a monoid? Yeah, it's just another instance of a number or string or list is the same. And yeah, this is quite fun actually.
Yeah, I'm thinking about it, and I think I didn't even know that this theory existed, but somehow I felt it had to exist. But I didn't. I also didn't know like how much theory can you apply to that, like how much beyond what you just mentioned, how much deeper can you go? And I'm sure if there's people dedicated to that, you can go much deeper. But then, what's the usability of this for a normal programmer, like in your day to day? Like,
I
do
have
you
to
really
say,
need that?
I have to say that if you're familiar with it, it helps you go faster, because if you go, for example, if you get into Haskell or like the more functional parts of Scala, a lot of the code is basically written in this way. Like everything is expressed as some of these categories, right? That have these laws and stuff. If you're familiar with them, it's incredibly fast to convey really complicated concepts because you're already familiar. But if you're not, it's just gibberish. And that's where I found when I worked with some people who actually did more the theory part of category theory. and they were programming, but they were pushing it to a limit that I was not comfortable with. Like they were pushing it so much further, and I was like, is this necessary? Like, let's just do normal programming, And I guess this is how some people feel if I, talk to them about monads and monads and things like that. So I don't know. I think there's diminishing returns. I think some basic concepts are used every day. I think they're useful, like monads.
Mhm.
Nowadays, even at Factorial, we use them, and pretty much everyone understands how they work more or less. But deeper concepts, I don't know. I think there's diminishing returns, like with everything.
Yeah. And you also mentioned functional programming. I guess that's against object-oriented programming, or are there any other paradigms that we should think about?
Yeah, against imperative programming as well. And so in a way, the functional programming kind of bias for me was thinking of everything as data structures. You express everything in a data structure, and then functions that just transform these data structures, and try to not mess with state, try to make everything immutable, and so on. This was really fun when I worked for a number of years with Clojure. And in Clojure, everything is basically a dictionary, like a very simple data structure, and then just a bunch of functions that operate on that. And because you only have to learn one data structure and everything's expressed like that, I feel you are much more productive in the end. You build up your vocabulary if you want to deal with these data structures, and then you can be really, really productive. That's the feeling I got with Clojure. Probably it's basically, I never got it with any other language. I felt so productive. And Clojure is another cult, by the way. It's a great, it's a great one, but it's still a cult. It's hard to get into. It has a learning curve, and it feels like everyone says the Clojure is just the best, and with Clojure you don't need anything else. But it has a lot of merits to it, and the community is amazing as well. So, yeah, I miss it.
And what about the graph in the graph community, or the graph? The community.
I don't know. I haven't been in touch too much with the people who are obsessed with graphs, and I'm curious about it. Lately, I'm diving a little bit deeper into graphs because, I've been playing a little bit with Neo4j, kind of to use it as a knowledge graph, basically to use with LLMs. We can talk about it later if you want.
Yeah.
But yeah, I need to get more into graphs because I think there's something that some people know that I don't, and I want to dive deeper.
Yeah, I remember the first time we used graphs. We're trying to build a marketplace of people, skills, projects, and we thought that by creating a skills graph connected to people and to projects, we could potentially find those relationships and be able to make better recommendations. But I don't know. Maybe potentially there are other solutions for that. But yeah, I love the idea basically. But then at the point, we had some issues with historical data. We didn't know how to manage that properly. I don't know if that's really an issue or just we didn't know how to do it at that point.
Something I want to explore a lot is the basically neural networks on graphs. So graph convolutional networks, basically. I've been really captivated with the idea of building a graph with business domains, because a lot of them can be modeled like graphs, like skills, people, and connections like this, and basically compute basically node embeddings. So for a specific skill, for a specific person, compute embeddings that depend on the relationship to other nodes in the graph, and use that for some downstream task, like to predict something or to classify or recommend something. And that's something I want to really dive deeper into. I think it could be cool.
Yeah. Well, I think we're going to get into some definitions of embedding. Well, I was thinking to ask you afterwards about embedding versus other models to retrain and to use as memory for what you're trying to do as a task. But before that, you've mentioned a bunch of technologies and that you've been playing with most of them. Like how? Either when do you have the time, or how has your career allowed you to do that, basically? Because normally, like, you get in a job, and yeah, if they use React as a front end library, and then if they use Node.js in the backend, that's what you're going to use, and that's it. So how do you play with other technologies?
Yeah, that's a very good point. So I've been in a very unique position in which basically I started a company with two colleagues. Julia Jama was one of them, the kid I mentioned at the beginning. And we started a company that was an agency. And then we were focused on Ruby on Rails, which was really hot at the time. And it's kind of hot still, I guess, in a way. And we did most projects in Rails. We were very specialized in that. But quickly I got bored of Ruby on Rails, and as soon as I could, as soon as I could, I got into exploring other languages. First, just to for fun, but then quickly I started looking for projects, paid projects, basically in those languages, and that for me has been the lifesaver over and over again. Whenever I wanted to learn something new, usually I just looked for a project in that technology. I got just a basic familiarity with it, and I got into the project and learned really quickly there, because it's like if you're working with other people who actually know that technology, you learn really quickly. And that's happened with Clojure. I got into the Clojure community um, in when I was in Berlin. Actually, it was kind of the decision to get into Clojure was I went to a conference actually on Clojure. I'm like, okay, what is this? You know, it looks cool. And I went to the conference, and the things they were talking about, they looked like they're talking about things from the future. I had no idea what they're talking about. And I'm like, this is weird. Like I thought, I knew programming, and Ruby is, and this was so different. So I decided to get into it, and ended up working on a bunch of Clojure projects. And then later on, actually, I got into data engineering. So I was really curious into getting deeper into data engineering. And at that point, I was quite lucky in London. I was in London. I had been working with Clojure professionally for many years at that point, and then I kind of traded my Clojure skills for data engineering, for a data engineering job in Funding Circle in London, a company called Funding Circle. Basically, I told them I want to be a data engineer, but I don't know data engineering, but I know Clojure, and you're using Clojure. And they're like, okay, so you teach us Clojure, and you can work as a data engineer. I'm like, great.
Good trade-off. Well, I have a bunch of questions. First one, you mentioned in the conference, in the Clojure conference, they were talking about things that looked at like if they were part of the future. Like what kind of things were they talking about that you thought like, hey, what's this is amazing?
It sounds really dumb now because now it's so ubiquitous. But at that point, there was this library called Core Async, and it was kind of a coroutines library. And in Ruby, we'd never heard of anything like that. Like in Ruby, the concurrency parallelism story was terrible, absolutely. So we'd never heard of anything like that. And it looked really fancy and really new, even though it's really basic. Nowadays, everyone has coroutines, and it's a classic thing.
Okay, and then going to data engineering. What's a data engineer to begin with? Like you were good at Clojure, and then you wanted to be a data engineer, but what that mean?
Data engineer is just a person who takes data from point A to point B. That's it. So it's really simple, but it's actually deeper than it seems. So it's hard to get the data from point A, transform it in the right way, get it to point B in a timely manner with specific latency requirements and so on. So there's a number of technologies. There's obviously batch approaches which are more traditional, streaming. And in that job, actually, we were doing streaming. I suspect that we didn't need streaming, and that was something that was talked about a lot in the company, because streaming is kind of like
for streaming.
No, it was there. It was already there.
Okay.
I didn't do anything, I promise.
I want to try. Like, were you using Kafka or any other?
Yeah, we were using Kafka streams to transform Kafka topics, and it was cool. But I suspect it was a little over engineered. Maybe now maybe they've achieved bigger scaling and it's paid off. At that point, it felt that we could have done away with just batch. But yeah, it was really fun. And the best thing for me is there I learned a lot more SQL, because the SQL I had been exposed to, it was quite basic. As a software engineer working on Ruby on Rails, you will find that a lot of people have very basic SQL skills, because you never have to use SQL. Never have to think about it, and then when you actually have to think about it, you don't have the skills. So it's pretty terrible. And there I learned from some people who knew a lot of SQL, and they were like really, really, really good. I'm really glad I worked for them. Yeah.
What's the difference between a person that knows a little bit of SQL and someone who really knows SQL? I mean, I don't know, SQL sounds like one of those languages that you can just know the basics and you will do fine.
Yeah, I do think that actually getting good at SQL is not that hard, but staying pretty mediocre at SQL is also pretty easy. So if you just know how to do one type of join, because that's the type of join you always do, and and that's it, then yeah, you're going to go very far in the world of Ruby on Rails applications. But then if you get a little bit deeper, for example, with window functions and things like that, and then it can get really, for me, window functions were one of the harder things to actually get. But yeah, then you feel more confident. And when you have to query anything, you basically, it is not really that hard, to be honest. But you have to want to do it. I think a lot of people, they dismiss SQL as something that they don't need to learn, but I would advise against it, actually.
Okay. Then you're working as a data engineer. How did you start with AI? When did that happen?
So I was starting, as I mentioned maybe a little bit earlier, like just reading some books, because I'd always been interested. And in fact, I had done the Coursera course, right? And I had some concepts like logistic regression and things like that, some basic stuff. And in Berlin, when I was working in a project that was kind of an Airbnb clone, I remember that basically logistic regression was the thing that I had learned that week. And I decided to apply it to a problem without really knowing any other techniques to apply. So basically, that I had that technique, I'm going to apply it. And it actually was pretty fun, because it wasn't that, and that basically we had a ranking of the apartments, basically, when you do a search. And the ranking, it was basically random, basically. So just by adding a little bit of logistic regression and trying to,
How
for example,
random? Like, I'm thinking, how
like I think
what's the
it
logic?
wasn't like maybe sorted by recent, most recently posted or something like that. So it's basically not related in any way about the quality of the apartment or how much, how many bookings it had or anything. So it seemed like a really low hanging fruit to fix, right? It was like, as long as you give a ranking that is better than most recent or whatever, should work. And we made a very small model that basically predicted, with the number of bookings, basically it ranked it higher, basically. So it predicted the number of bookings, and that we ran A/B tests. So that company was really good at running A/B tests for everything. We had a lot of A/B tests. So we started doing A/B tests on that, and it seemed to work really, really well. Unsurprisingly, right? Because we the previous approach was like completely naive. And I was super happy. And actually, that was the beginning of a machine learning team in that company. So we hired an actual machine learning expert there, and they started kind of improving the model and so on. And I remember the guy was like kind of laughing at the, why did you use logistic regression for this? I'm like, it's literally the only thing I knew. So that was fun.
So logistic regression, it's machine learning. So let's get into basic, really, really basic definitions. And I guess a lot of people, or people who are familiar with AI, like already know, like, okay, AI, what's deep learning, what's machine learning. But can you
I can go
those
through kind of the very simple intuition behind, what's the difference and all this stuff. So machine learning is basically learning from data, right? So it's a machine learning model is really just a program. Okay, bear with me with that analogy, because I believe it is a program that basically learns from data instead of being handwritten by a programmer. So when you write a program, you already know the rules you want to apply. And when a user, puts their login and their password, then you log them in. And that's a program that you write, right? And that works well for things that you know how they should work exactly. So if a user puts the login and the password is wrong, then you tell them it's wrong. It's like simple business logic that you can just write. But in many cases, there's logic that you cannot write because the data is it's kind of a distribution of data that varies a lot. So for example, if you want to classify an image for cats and dogs, the classic example, you cannot just look at every pixel and say, if this pixel is red and this one is black, then probably it's a cat. No, it would be such a huge program that you would have to write, and it would be very brittle because you've probably looked at 2 or 3 images and it works well for those. So machine learning lets you just feed that data to a model and basically have the model become a program that is basically generated by a learning algorithm. So in this case, a classifier that looks at pictures of cats and dogs, keeps classifying them wrong, and kind of gets better at classifying them until you're happy with the model. And then at that point, if you feed it an image that is more or less a distribution of images that it's seen in training, it will work, right? With certain accuracy and certain parameters.
Do you need deep learning for that? A neural network, or can you do it in another way?
I mean, with images, now it would be pretty not a good idea to not use deep learning, because that was like many years ago. I believe it was, when was the ImageNet moment? Was it 2016, 15?
Yeah,
Something like
around
that.
that.
At that point, basically, it was considered that computer vision is solved, in the way that basically deep learning has managed to train a model with a bunch of images and then classify them into classes, and it just works. Okay, before that, images were a bit complicated. But machine learning was still used for a lot of things. Like in tabular data, for example, even today, machine learning is still used, because tabular data, it seems kind of dumb, but tabular data is very, very ubiquitous everywhere. And it's really not a great fit for deep learning yet, at least. So it's kind of the last frontier, I believe. Now there's some transformers that look at tabular data, but people still use gradient boosted decision trees, which is a kind of best of both worlds kind of, that is widely used in production today. So this is still machine learning and still something that people use. But let's go back to what machine learning is. So it's a model that learns from data, but the data is something that you have to kind of craft a little bit. You cannot just give it raw pixels. That's not going to work. So what people do with machine learning is they create features, what they're called features, right? So for example, if you're classifying likelihood that a user would buy a new product, for example, and you have some data from that user, you have their age, you have the date of their last purchase, and things like that. If you feed that to a machine learning model, it might not be able to find relationships between the last purchase date plus the age plus the season of the day of the month plus something else, right? So you need to sometimes be smart about it and create features that represent these, kind of summarize these ideas. So for example, you could create a feature called end of month. Okay, so that means if the last purchase was end of month, then yes, otherwise no. And with this feature, yes or no, the machine learning model has some opportunity to use that yes or no to give you a better answer. And that's what's called feature engineering. And a lot of thought goes into it, because you have to really know the data and the domain and what you're doing and the things that could be affecting the purchase and so on. So subject matter experts matter a lot there, because they will help you create the best features and so on. And
I
in a
was
way,
going to take
yeah,
my product manager card here and say, hey, but product managers are the ones that actually know what features could be relevant, even though
exactly.
might be that we believe some of the features are relevant, but then we see that they are not, that there's no correlation.
Exactly. And that's basically a human endeavor. You need to understand the data, and the better you understand the data, the best features you have, then you'll get a better model, right? And that's traditional machine learning in a nutshell. And deep learning, what gives you basically is models that are much bigger, so a lot more parameters, because in the end, a machine learning model is a bunch of parameters, basically. And they're called kind of weights, right? So a bunch of weights. Deep learning models have a lot more weights, and then because they have that many more weights, they can learn from a lot more data. But the main advantage they have is that they engineer the features automatically. Okay, how do they do that? Basically, it's pretty simple. So deep learning models, they're called deep because they are a bunch of layers. They are neural networks. Neural network is a bunch of layers sequentially arranged, and then the input goes on one side, and then a bunch of computations go on, matrix multiplications go through all these layers until you get the final result. Maybe cat 40% probability and dog 60%, right? Now, these layers have a meaning. Why there are deeper layers is because they create hierarchical representations of the data. So in a way, it's similar to our visual cortex. So our visual cortex is very well known that at the kind of earlier layers, you see just like kind of light and dark pixels, so to speak. And then the next layer identifies some edges, right? So edges like horizontal or vertical edges. The next layer identifies like some kind of curve. Some layers then identify circles and different shapes. And then eventually, excuse me, eventually you can identify really complex features, like, for example, animals or even faces, right? This is thanks to that composition. So you start with points and then edges and then curves and so on. So deep learning models learn provably, actually, because this has been inspected, these kind of hierarchical features. So what's called convolutional neural networks are kind of computer vision model, they learn at the beginning lines and then edges and circles, and then at some point there's neurons that detect dog eyes, for example, or dog ears specifically, right? So a combination of edges and circles in a certain part of the image. So this is really convenient because if you can learn the features from the data, from the raw data, you don't have to do feature engineering. And that basically is a lot of work that you don't have to do, and it works better. So that's kind of the main difference between machine learning and deep learning. And also the fact that with deep learning, you can feed it more data because there's more parameters to tweak and learn. And with machine learning, basically, it's not as easy to scale. If you have much more data, it's not easy to make a better model that won't overfit. So, yeah.
Do you need to train both the deep learning and the machine learning models? And how much data do you need to train them, and what kind of data do you need to train them?
Obviously, you need to train both. And basically, the rule of thumb is like if you don't have a lot of data, you can try machine learning, like traditional machine learning. If you have a lot of data, it only makes sense to use deep learning. But this has changed a little bit because now we have pre-trained models on so many different kind of base domains, like, for example, vision. So we have these models that are pre-trained on seeing all kinds of images. And even with a little bit of data, you can already fine-tune, what's called fine-tune the vision model to be good at the specific tasks that you want to give it. And with language, that is now even more true than ever because we have these crazy language models that know so much about language and about so many things in the world. And by fine-tuning them on specific tasks with very little data, that would be basically impossible. And even machine learning models couldn't do it at that point. You can get really good results. So I know I'm biased because I love deep learning, and for me it's the hammer that I want to use for everything. But I do think that deep learning is slowly but surely making everything else in machine learning irrelevant. Slowly but surely, I think.
I want to get more into the intuition of what these models are, and the fact that they have that they are neural networks, the shape of it, the architecture, and I think we can learn from that. But before we go there, on the layers, that's a question that I never really got to ask myself. But is there a science to the layers, the size of the layers? For example, in convolutional neural networks, I think there were like different types of layers that you had to for getting the right results. How does that work?
It's an art.
It's an art.
It's an art. You'll find a lot of tricks, and basically ex post facto you can detect problems. Like, for example, I'm sure when they invented skip connections, for example, which is a huge breakthrough in computer vision. There are these basic connections that instead of going through one layer, there's some information that skips and basically is added, skipping one layer, basically. And that sounds like why would you do that? And I'm sure they had the intuition that the problem is that the gradients weren't flowing properly. So how neural networks work is that you train them with a forward pass. So you give it an image of a cat, and then you get the answer, which is 40% cat, 60% dog. Now, if you know that's a dog, you want 100% dog, not 60% dog. So you tell it, and then there's an error. There's a kind of a 40% missing. And that error is propagated layer by layer in what's called back propagation. Okay. And those are called those values that basically tell how much you have to tweak each of the weights so that were responsible for the wrong prediction. So it's kind of correct the mistakes it made. So how much you have to tweak them, these are called gradients. Okay. And the gradients that flow back in some architectures, you could have situations in which the gradients kind of lose signal and they stop flowing back. And then you don't get enough signal back, right? And this, I guess, was the intuition, like knowing that this was happening, probably was the intuition behind, hey, what if we just add like an information highway so that instead of going through this kind of path, it has another path to go through, and then the gradients can flow more freely. I'm sure things like that come from a proper intuition, but I'm also sure as well that a lot of the tricks that exist in neural networks today are fruit of just experimentation. Like, let's try this, let's try that. Ooh, it seems to work better. And then later you sometimes discover maybe the theory behind it, and there's mathematically inclined people that will actually find why something is like that. But a lot of it is feels more like engineering. Like, let's try to tweak this here and there, and it seems to work better. And we might not have the physics to explain that, but we just know it works. You know?
Yeah.
Um,
I think this kind of like life, like we behave, we act, and then we tell stories about how we act. So we try things, and then we try to find the theory about behind those things.
Absolutely.
Yeah,
Yeah.
yeah, go ahead.
No, no, no. I was gonna say there's a famous phenomenon called a double descent. That is something that I think took quite a long time to even have the theory to explain why it happened, but it was something that people just saw, right? It just happens. And it was a phenomenon where you were training, and then the loss, which means the error or how badly the neural network
Mhm.
is working, it went down for a while and then stabilized. And at that point, you would think, okay, that's it. You cannot learn anymore. But then after a while, it would go down again. And that is kind of it was a mystery for a while, but it was just something that you knew would happen. And yeah, and then finally, I think there was some theory behind it. Like this phenomenon called, there's this paper called grokking. I really love this paper, but is this idea of like you train something for long enough, and eventually there's some shift in the network that makes it suddenly perform much better. Okay. And this was quite a mystery, but then it was posed that basically regularization was responsible for this. And for me, that's actually something that tells you a lot about intelligence in general, I think. Because in my experience, when you learn something, you're making a model of how it works, right? So for example, you learn chess. No, you're learning chess, and you're learning all these strategies and all these openings, and you have this complex model of how it works, and it's quite complicated. You keep forgetting details, and like it's hard to get it. But then you feel you play with an expert, and the expert has this kind of intuition that is already discarding 99% of the moves at every stage. So you're still considering them because your model is too complicated and you need to evaluate them. But their model is really simple. And they're like, okay, this is a bad position. This is a good position. And it's really, really fast. And I think the reason why that is because basically they've been compressing and compressing the models to the point that they are very simple and they are very kind of fast to execute. And they've really grokked the chess or whatever they're learning. Grokking is a term that's used in engineering for when you really understand something deeply, when you really get it in your bones, basically.
And this grokking applied to the models, does it mean that we reduce the size of the models while keeping the performance?
It means that the performance goes up because somehow in the weights inside the model, a better path has been found, a simpler
Okay, sorry.
path.
When I mentioned performance, I didn't mean the execution performance, but actually the
The
results
quality.
performance,
Yeah,
the
yeah,
quality of
exactly,
the result.
exactly.
Okay.
That's exactly right. And that's something that also intrigues me a lot about these models, because there's this idea of the lottery ticket in neural networks, which is that you train this massive model with all these parameters. You start from random and you keep tweaking them until they work well. And then you realize that most of the weights are actually very small and have no effect on the actual quality of the output. So it's kind of a waste that you took all that time trying to tweak them, because most of them are useless. And in a way, you can see a sub network inside the neural network that's actually doing the work, and that's the one that works, right? And at the beginning, when this paper about the lottery ticket came out, they were posing like, is it possible to know what sub network is it going to be, so that we don't have to train the whole model and find it at the after? And there's some work in that direction, but basically that tells you that neural networks are very sparse. So most of the weights are doing nothing really. And that's thanks to that fact. There's a lot of techniques nowadays, very very popular techniques of like distillation and quantization and all this stuff, because you know that you can remove most of the information and it still will perform well, will have good quality. I find that really fascinating, I think.
Yeah, I remember the first time that I heard about distillation. It was, I think, 3 years ago when I was working in another company, like where we were doing NLP models, and the engineers were telling me about, yes, we're distilling the model. I couldn't. That's why I was asking about the quality of the results. Like I couldn't understand how you can reduce that much the model and still get the high quality results. So I think it is amazing. And you mentioned, well, yeah, most of the neural networks, like you see, the most of the weights are zero or almost zero. does that also apply to the LLMs that we are playing around these days, like GPT, or do we have that information at least, or I don't know?
I don't know that we have that information, but I would guess 100% yes. Like there's no
Same.
reason to not think. And in fact, that actually is almost provable in the sense that there's a problem with large language models that you can see that they are very sensitive to adversarial attacks. So adversarial attacks are a really fun or interesting property of neural networks. That is that sometimes if you give them, for example, an image of a cat, let's talk about the classifier cats and dogs. You give them an image of a cat, and for most cats, it will say it's a cat. But if you take an image of a cat and you change 2 or 3 or 4 pixels and you make them a little bit darker, then suddenly you might be able to make it think it's a dog, even though a human will see the picture and won't even notice the pixels that change, right? And that basically tells you the model is very sensitive to perturbation. So any kind of change or noise in the input will completely make it go crazy. And this is one of the reasons for this is that because a lot of the weights are not really used, sometimes you can find a path that is basically not very well traveled and that completely gives you confidently the wrong answer. And if you're able to find that path as a hacker or like someone who wants to break the model, then you can craft these images that will completely break the model. And in large language models, this has been done. And it's really strange. It's like you ask it a question and then you put a bunch of weird characters and weird words, and suddenly the model behaves completely different and goes into a different direction. And this is a bit scary because it's like very sensitive to hacking.
Yeah.
But
Do you
we
have
found a way. Yeah.
Do you have an example, a funny example of that?
Actually, I would like to share with you later some links because
Okay.
this link is pretty interesting. It shows how you ask a question. Especially these people were targeting the kind of alignment part of the model. So, you ask it to do something really bad and it will tell you, no, I can't. And then suddenly you put some characters and it will happily tell you everything you need to know.
Nice.
So strange.
Yeah, I think we skipped a part that I also wanted to know on the basics of deep learning, AI,
Right.
like these concepts, supervised versus unsupervised learning.
Okay.
What's the difference?
I mean, supervised is I would say the best case scenario. So if you have a bunch of data and you have labels means what you're trying to predict, you have it. So for example, if you have a bunch of images and you already know if they're cats or dogs, then you're in heaven basically, because neural networks work really well. If you already have labels, you can teach them, this is a cat, this is a dog. And then eventually they will get what makes a cat and a dog a dog. So that's great. And that's basically what you learn mostly when you learn machine learning is supervised methods. But unfortunately, the world doesn't work like that. No one has supervised data. This is just a dream, okay? So companies don't have supervised data. So I'm much more interested in methods that are either semi-supervised, which means you have a little amount of labeled data. You can pay people to label data for you, and that's what some companies do. But it is expensive, and it takes time. So you might choose to have that for a small part of the data, and then use methods to basically infer the rest of the labels, so that it still works. But for me, the most interesting one, and the thing that kind of is basically what is changing everything in the past few years, is the self-supervised training. So self-supervised learning just means you have data, and somehow you create a model that learns from that data without anything else, just with the data itself. And the way it does that is basically doing some kind of puzzles on the data. So to give you an example with language models, right, which is what we see nowadays, the language model, the classic language models like GPT, all these, they learn on what's called the language modeling objective, which is kind of a task that we give these models to learn. And what we give them is, if we have a sentence, for example, we give them just the whole sentence without the last word. And then we ask them, hey, predict the next word. What's the last word? And this is kind of a game that they learn to play, and they get better and better at doing that. And this is what makes ChatGPT and GPT-4 and all these models as good as they are. Just predicting the next word given a sequence of words. And this is, I think, quite fascinating as well, because back then, I think when I started looking into that in 2018, I think is when Jeremy Howard from FastAI was talking about ULM fit, like universal language modeling and fine tuning on top. And somehow this idea that just by predicting the next word, you could actually force the model to learn about facts about the world and about deeper concepts in our world, this to me seemed completely science fiction. Like, how can it be? No, like, is that really true, or is it just an illusion? And at the time, I mean, there's people who still think it's an illusion, but I think it's really hard. It's getting harder and harder to say that this is an illusion, I think.
Yeah, from an intuition perspective, it seems difficult to believe, actually. Like, you're training a model to predict the next word, but then how does it know if it's the right word? And like, I don't understand.
So when you teach it to predict the next word, you already know the next word because you have the full text, and you just hide it for the model. And then the model just needs to kind of adapt its weight so that next time, given the same context, the same text, it will predict the right word. But now, if it's just a bunch of numbers, it seems like it's just a statistical game. It's like you adjust all these numbers, and finally you will be kind of like a parrot, right? You will hear that thing long enough so that you will just predict the next word correctly without understanding anything of what you're doing. But what seems to happen in these big models is that they have so many weights, so they have so many billions and billions of parameters that they can tweak, that they end up learning general algorithms within the weights. So they learn, in a way, not just mappings from words to words, but rather almost like programs, in a way, that let them solve like real problems. Like, sometimes it feels like they're reasoning, and in a way it's because they're applying these functions, these programs that they learn. So, taken to the philosophical kind of end, you could argue that technically, in a big enough model, you could learn any arbitrary function, including, for example, a reasoning engine or a limbic system like the one we have, or anything, an emotional, system that basically certain words trigger emotions that trigger, downstream cascading effects, and then they end up. You could implement anything in those ways, like, technically, okay, philosophically, you could learn anything. And to be fair, it's really hard to know what's in those weights. So I think a lot of speculation about what these language models actually learn is totally fair, because we cannot really prove or disprove many of these things. Some people say, oh, there's, they are conscious, they have consciousness inside. And, I don't think it's a disprovable claim because also we don't have a definition for consciousness. But yeah, I tend
That's
to think it's
correct.
not. But
Mhm.
yeah, it's really interesting.
Yeah.
Actually, oh, sorry.
No, go ahead.
Okay, I was going to mention a really cool paper that came out a month ago, that really blew my mind. It's this paper, I think it's called Language Models Are General Pattern Machines or something like that, or General Pattern Modelers. And this really blew my mind, because what they did is they took a large language model like, GPT-4, and then they just gave it, actually they took GPT-3, so quite an old one for the standards of today, and they gave it just sequences of things that have no meaning, except they model, for example, the states of a robotic arm. So, like, this is a state, and then you have to produce the next state. Okay. And basically they fed it this information in a way that it learned a relationship between these states, these kind of sequences. And it could be a robotic arm, it could be like a time series of like values, for example, the price of a stock, for example, right? And it would learn and to model that sequence, all in context. So you didn't have to train the model. The model is already trained. You don't have to do anything to it. Just give it in the context all these things and tell it, predict the next value, something like that. And obviously, this cannot be memorizing a sequence of things. It's never seen those numbers before in that order, So somehow it's learning these general sequence modeling algorithms within the weights, which is, to me, it's absolutely fascinating. Like, I never expect that this would be the case with GPT-3, which I already consider quite outdated. No?
Yeah, there are so many things about these large language models that are so surprising. I don't know if it was a paper or just an article that I read where they asked, I think it was all the to I think ChatGPT 3.5, all the the coastal lines of all the continents, and it basically gave the coordinates of all the coastal lines. And that's not something that it keeps in memory. Something that it's difficult to understand how magic that is if you don't understand how it works, because it's okay, it has the information stored. No, that's not it. Like, the model actually knows that, and it's amazing. I don't understand how. Do we have visibility on those models? Like, how do they actually work? Like you were mentioning, like probably there are like sub networks that do certain algorithms and things like that. Do we have visibility on that or not?
No, and that's a shame, I think, because so when GPT-2 came out, I don't know if you remember, it was a few years ago, but the thing with OpenAI was like, oh, GPT-2 is really dangerous, so we're not going to release it. We're only going to give you the smaller models, and eventually they gave us all the models for GPT-2. GPT-2 has been a source of amazing research. Like, so many people have kind of got into the guts of GPT-2 and tried to figure out what it learned, what everything did. And I think that was amazing for language model research. And
Maybe
from GPT-3,
just one question
yeah,
on GPT-2, like how much data was used for training?
I don't remember actually. Yeah, let's look that up, and I'll post it later. It's kind of super small. It was huge by those standards, right? Back in the day. I remember that it was the first demonstration of a language model creating a story. I think it was a story about unicorns and like something like that, and everyone was like, "Oh my god, this is insane!" Yeah, it was really cool.
Wait a few months and you'll see.
Exactly. Yeah, so for me, it's a shame that GPT-3 was already closed and they never kind of published anything. They did publish a paper with quite a lot of, at least the results of the benchmarks and so on. It wasn't too bad. Much better than GPT-4, because GPT-4 was just a marketing brochure. Basically, there's no paper and nothing. It's a shame, to be honest. But I'm happy that Llama 2 from Meta is out, because this is really going to help research and like understand these language models much better.
I think we skipped one topic.
For sure, I'm
basics
sure.
as well.
Jumping all the time.
Transformers. It's one of those other words that I think that need definition.
Okay, yeah. So I think kind of to understand, why the jump, right? Like, what is this thing that wasn't there before? And the key is transformers, right? So basically, before transformers, before attention, there was language modeling. So this was something that was done, for example, for machine translation. So machine translation is a classic problem where you have to translate a sequence to another sequence. So you have a sentence in French and you have to translate it to a sentence in English, right? And for that, basically, you have to read the sentence in French and then produce the next token, and then the next one, and then the next one in English, right? So before transformers, usually recurrent neural networks were used, okay? And recurrent neural networks are a kind of neural network that will consume data one piece at a time. So for example, the French sentence, it will consume one word at a time. And as it reads the word, it kind of updates a representation, a small compressed representation about what's going on, basically. And it's similar, I like to say it's similar like a conversation. So you're talking to someone, and as I say words, your brain is creating a model of what I'm saying, and it keeps updating it. But the problem is, if I keep talking, you probably don't remember what I said 2 hours ago, and probably it's out of the model because it's no longer relevant. So this is a very kind of, it's what's called a bottleneck. It's something that if you keep feeding it data, eventually you will have to forget data that is not relevant or that it's old. So basically you lose track of what happened much longer time ago, no? And this is a problem when you're trying to work with long documents. So for example, if you're generating text, like stories that you can generate with GPT, by the end of the third paragraph, you still need to use the pronouns and the entities and the things that you mentioned in the first one. If you keep kind of reading and forgetting what happened at the beginning, eventually it's incoherent, basically, a text you will create. And that's a problem that happened at the beginning with these recurrent models. And then the solution was, so if these recurrent models are a live conversation that you have to kind of pay attention, but you have a limited working memory, the solution was attention. And attention is basically making these kind of steps of paying attention to each part instead of kind of letting them fade out in time. Or in the case of LSTMs, it's a little bit more sophisticated. It's a recurrent neural network that decides what to keep and what not to keep. But eventually it has a limited memory. So eventually we'll have the same problem. So instead of doing that, you lay out all these things and you have them in what I like to say it's a piece of paper. So instead of me talking to you, I will talk to you, but I will give you a piece of paper and a pen, and you can write down everything I say. So at any point of the conversation, you can refer back to everything I said. And actually, you can refer back to a specific concept that is now very relevant that I mentioned 2 hours ago because you have a piece of paper, right? And that's a big game changer. And this piece of paper is basically what we call the context size. So these language models, they have a size that you can put text in, and you cannot go further than that because basically they don't have enough memory, okay? And this is what attention lets you do, is within that context size, you can always refer to any part of the text to decide what the next token is. So you have perfect recall, basically. You have the trick that you're basically noting down everything. And yeah, that's a game changer because that means that if you keep training with longer context size and longer context size, you can eventually process entire books in which the last word can still see the name of the character in the first paragraph in the first scene. No, and that's, even in a way, it's much more powerful than how we process data because we don't have that luxury. We cannot keep everything in memory. We have to kind of forget things, and we have to go back to read them. So something non-intuitive about these models is that whatever they do, they can look at all the text at once the whole time, and this is thanks to attention.
This is thanks to attention, but is it the same as transformers get us that attention that we need?
Yes, so transformer models are basically, there's different kinds, but for example, the encoder-decoder models, they encode something and then decode it. The GPT models, they are decoded only. Okay. And what they do is they keep looking at the text that they've generated in what's called self-attention. And they always it's called attention because what they do is literally pay attention to what's most relevant right now. So for example, for a specific word if they have to generate a pronoun, for example, they will pay very much attention to the noun that they're trying to kind of refer to, right? So if that noun is a dog, or if it's a specific gender, then the pronoun has to be in a specific way. So that way they can decide what's important and what it's not when they generate each token.
Speaking of attention, and before we continue with large language models, are there any other deep learning models that we should pay attention to that are not LLMs? Or currently the only thing that's really interesting is LLMs and we should just go deeper into that?
That's a hard thing because there are some alternatives to LLMs that also model language, but in a different way that transformers do. So one of them is called RACUV, I think, RWKV, and it's supposed to be pronounced RACUV. I don't know why. But it's, if I understand correctly, that model is kind of trained like a transformer, but the inference, so when you ask it questions, it works like a recurrent neural network. So it doesn't have the problems of the context size. My question, though, and I still don't understand how it works, is how can it be? How can you get the best of both worlds? But they have a long explanation in the repo. I can share the repository there as well. I think it's quite interesting. And I mean, I think there's some other interesting things. So, for example, I'm a fan of this thing that came out a few months ago called liquid neural networks. Is this guy called Ramin Hassani. I really recommend any videos by him. He does a lot of TEDx talks, and also he has like kind of longer deep dive videos, and it's really cool. It's something pretty complicated, but the idea, I think the main idea, is replacing the normal layers of neural nets with differential equations. So if each layer of neural nets, they can perform simple matrix multiplication operations, instead of that, if you give them the power of a full differential equation, they can express a lot more. Especially they can express change over time much more easily. So
that's somehow, for each node of the layer, or for each layer, like what do you replace?
I'm not sure. I think it's for each layer, but I haven't really understood it yet. So what I got from that is that it can process streaming data or sequences much more naturally. Okay, so for example, it can process video with much fewer neurons. And they used it, for example, to do some kind of basically reinforcement learning for aviation. So they took a drone, and the drone kind of consumes video, and then it behaves, right? And they managed in their demos, which, I mean, there are still demos in the end, so you don't know really what's going on. But they claim that you can use very, very few neurons, like as little as 30 neurons, to drive a drone or a car, which is, I mean, sounds completely outlandish. But the best thing about this is because there's so few neurons, it seems to be much more robust to the input and much more kind of, it learns much better and stronger representations. So it doesn't have the problems that we mentioned before, the adversarial attacks, where if you add a little bit of noise, or if instead of day it's night, or if it's raining or not raining, then suddenly nothing works. That's what's happening with a lot of neural networks today, right? That's why it's so hard to do self-driving cars as well, because the data distribution is so wide. So it seems that this is promising in that direction, and I'm super excited about it. What I don't understand is why is not everyone talking about it? That's my question. Does everybody know something I don't? Is it obviously a lie? I don't know, but I think
There are
you
two
should check it
reasons
out.
potentially. I mean, and I have a question as well. I mean, one reason might be like everybody's just focused on making money with LLMs, so
Yeah.
creating service layers on top of LLMs. So who
Yes.
cares anything else right now? Let's exploit that. But then I'm imagining, and maybe I'm missing the point, but and I don't know anything about these liquid neural networks that you mentioned. But the current models, we have the neural networks, and we have very basic functions within each node, right? Like we have like the typical, I think it's which ones are normally the three functions that we have in the nodes?
So we have matrix multiplications, right? And then we have activation functions that are these
The
non-linear
activation
items.
function,
So you
yeah.
have ReLUs and leaky ReLUs and LUs and JLUs and the whole shebang.
So the I guess the liquid neural networks, what would be replacing are those, and maybe the training would be much more complex, I guess, because if you do the back propagation with those with derivative functions, I think, I don't know how that can work.
That makes it much more complicated. It seems that they found, so at the beginning they used differential equation solvers to do the forward pass, which to me it sounds like it must be really expensive to do, right? But apparently eventually they found some kind of closed form solutions to the equations so that it's much faster to compute. Still, I haven't trained any of these, but actually they have the code available. So I'm really, happy to go and delve and try to use it, because I think they're quite good at releasing the code and being quite transparent what they're doing. So yeah.
Okay. Maybe one topic that we haven't mentioned, that it's not LLMs, but it's the image creation tools that we have, and even video, like all these creative solutions, stable diffusion, and so on and so forth. Is there anything worth mentioning on that area that you believe we should be excited about?
I mean, these are getting better really quickly. Stable Diffusion XL, for example, it came out recently, and it's super powerful. As with everything, I believe that the open source models for me are the only ones that I pay attention to. I mean, obviously, I use GPT-4 and GPT 3.5 every day, but I'm mostly excited about the open source models, because those are the ones that we can trust in a way and eventually run and scale ourselves. Because that's another thing that I think is something that's changing, which is the price of operating these models and running them is dropping, and the price of fine tuning these models is dropping. So even though now it's not cost efficient to operate your own models, especially the biggest ones at scale, that's going to change. So like, I would say it's important to not get married to the proprietary models too soon if you don't have to. I mean, fortunately, most of the frameworks and things that are coming out are very plug and play. You can always change one LLM for another, and even there's tools that let you compare output by different LLMs. So I'm sure people are aware of that. But yeah, GPT-4 and GPT 3.5 are not the only ones, and Cohere and all these.
Maybe now that you mentioned how expensive that can be, can we have a sense on first training, how expensive that is in terms of compute, and then inference for the big ones, and also for any of the ones that you think are interesting from the open source community?
Okay, so training, I mean, I would say no one needs to train a large language model from scratch. So no one needs to do that except these big companies that are building their own. And these big companies are having a lot of trouble securing GPUs. So if you are thinking of starting a startup and having your own large language model, you might want to look into securing the infrastructure first, because that's going to be the limiting factor, and that's going to be the where all the money goes. So you need to raise a lot of money for that. But yeah, so that's just a use case for people who are building their own large language models from scratch, which is a very small minority. And then most people, if they want to train, they probably want to fine tune their models. And this is something that I've changed my mind a number of times on. And fine tuning the models, I think currently it only makes sense. It seems to make sense when you're fine tuning them on downstream tasks specifically. So, for example, imagine that you have a task you want to do with a language model that, for example, is extracting some data from a document, or, for example, summarizing reviews for your product, things like that. Okay. So in this case, if you manage to get a data set that gets the full review and the summary in the way that you like it, then obviously these data sets, you could generate them with GPT-4 as well, by the way. So this is a technique that is really cool. GPT-4 is so good that it could generate and label data for you, and then you can use that to fine tune another model. So that's something you can do, and it's pretty cost efficient.
Does that work? Like, I mean, what's the benefit of doing that? Because at the end of the day, you're fine tuning with the data that you're generating, and you're not even decreasing the size of the model. So just fine tuning it with something that the model already knew. What's the benefit?
So there's a number of benefits. So for example, first, if the model you're going to use is an open source model that may be quite a lot smaller. So there's a lot of things that are coming out right now where, for example, they show that Llama 2, the 7 billion model, which is very, very small by today's standards, if you fine tune it on a downstream task, it could be even better than the 70 billion model without fine tuning, which is really surprising. And even than GPT 3.5 and so on. So it's really surprising that fine tuning is so effective, even with very, very small models. And that might be something that you could be interested in. I think in this case, what makes most sense for fine tuning is with LoRa, which is a technique to fine tune a model in a very cheap way. So just to kind of establish the base, what is fine tuning? Fine tuning is taking.
Let's go with that.
Yeah, fine tuning is taking all the weights of the model, right? Technically, the traditional fine tuning is you have a 70 billion model, and then you choose some of the weights, most of them really, so the later layers, and then you keep tweaking them with new data that you give it. You keep the older layers, so the kind of lower layers, if you wish, you keep them frozen, so you don't change them, because as we mentioned, neural networks, they learn hierarchical representations, right? So if you're trying to teach a kid a new subject in school, you probably don't want them to relearn how to read. They already know how to read. So you don't have to teach them how to read. You just have to teach them the new vocabulary and the new concepts, right? So this is the intuition behind fine-tuning. You give kind of the most basic concepts, you freeze them, and then the newer ones, the ones on top, basically, you tweak them a little bit so that it becomes better at this new task.
Is there also a science in how many layers do you tweak, or how many nodes, or how do you do that?
If there is a science behind it, I don't know the science. So I still see it as an art. But yeah, maybe there is. I'm sure there's research on that for sure. Okay. But yeah, so you fine tune on downstream tasks, and then it becomes better at that, right? And then what you have is a model exactly as big as it was, so 70 billion parameters, but it's just better at whatever task. Now, this is a problem because it's still a lot of parameters. We're talking that maybe you are fine-tuning, you're tweaking 70 or 80% of the parameters, or even 50. It's still a lot of billion parameters, and that takes a lot of money and time, right? So there's a better way called LoRa. It's a recent technique that basically lets you, instead of training these kind of 70 or 80% of the parameters, it lets you add a little adapters in strategic parts of the model and freeze the whole model except these, okay? And these parts, you train them separately, and they usually represent a very small fraction of the total parameters. So it could be as little as 0.5% or 1% of the parameters. And then once you train these, they are made in a way that you can fuse them back with the original model. So then you get basically the 70 billion model, parameter model that knows how to do this downstream task. But I think the smarter way to go about it is to save these adapters and just kind of plug them in when you need them, right? And if you have, for example, multiple customers or multiple different tasks that you would like to use with the same big model, you can just plug and play different adapters. Okay, the operation of that is not as easy as it sounds.
Yeah, I was going to
And
ask about that specifically. Like, how is that plug and play that sounds so easy?
it is not exactly plug and play. So nowadays, basically, you will have to unload the whole model and load it again with an adapter. So you wouldn't be able to, for example, keep most of the parameters in memory and just switch the adapters. That would be really cool. Even per request, right? You could even try to do that per request. I don't, the engineering is not there yet, but I don't see a reason why this couldn't be done eventually if it's something useful. Yeah. So then what you get is, remember, GPT-4 helped you create a data set to fine tune your model, and now you have a mini model for each of your customers that is good at specific task, with a specific tone or language or data from your customers, right?
You mentioned mini model. How so? Like you fine tune it, but when you fine tune it, you reduce the model.
No, you get the adapter. The mini model, I mean
Okay,
the adapter.
the adapter. Okay.
Exactly.
Yeah.
Exactly. And in my mind, having an adapter per customer, for example, could be something feasible. If the operation behind, switching in and stuff, it would be doable. Yeah.
Maybe on fine tuning, and I had a point here that I wanted to ask, because I think for me, at least, from an intuition perspective, I don't think it has ever been 100% clear. Like, what's the benefit on the quality of the answers of the model if you do fine tuning based on, we're talking about summarization. So I fine tuned summarization versus embeddings versus just having a big prompt with everything explained. And maybe the summarization is not a good use case, but maybe we can think about another one where you could potentially solve it in any of the ways. Like I just fine tune my model to get the specific results, or I just have embeddings. So let's imagine the scenario where you've trained the model, or we have our GPT-4, right? That it's already trained, and we know it's been trained on a set of information, but we also want specific answers about that information. So we add an embedding for that with that information specifically, versus I fine tune it to get answers from that information, or I just add it in my prompt. Like, hey, here's all the information. Like, what are the differences between these three approaches?
Okay. So first, I'd like to define the embeddings just for the people who are not familiar with embeddings. So the idea of an embedding is, so first, what's the problem, right? Imagine that you want to have your entire help center, you have a knowledge base, of all articles on how to use your product. And you want a chatbot based on GPT-4 to answer questions about it. So the naive way would be you put your entire knowledge base into the GPT-4 prompt, and then you put your user question. Maybe they ask, how do I log out? Or something like that. That would be great because, as we mentioned, thanks to attention, GPT-4 sees the entire knowledge base at the same time, and it can find the article where that explains how to log out, and it will tell you how to log out. No? And then you send that to your customer, and they're happy. That would be great. But the problem is GPT-4 has a limited context size, as we mentioned. So also context size is hard to scale because of attention precisely. So attention has a basically quadratic cost with sequence length. So if you want to make it double, it explodes basically the cost. So that's why people are not releasing 1 million tokens context length that easily, because it's really hard. So basically with that limitation, you cannot put everything into the context, into the prompt, right? So what you need to do is put maybe just the most relevant parts of the articles that would help answer that question, right? And if you're a human, you maybe know that you should take the account login and logout article. But to do it automatically, the way is you take parts of your knowledge base and you basically compress them into a representation called an embedding. Okay, and you use a language model for that. So you have a language model read that part and then create a little representation of that. And then you use it as an index, basically. So the way you put it in a database, and then when a question comes in, you calculate the embedding of that question. And then that embedding acts almost like coordinates in some space. Okay, so each part of your knowledge base sits it's like a point in a space. Okay, you can imagine as a point in a space. And when some question comes in, that question is also a point in the same space. You have to assume that if the language model is good, the one you use for embeddings, the question will be closer to the topics that would answer that question. Okay, the topics that talk about accounts and log out and login, right? So if the question is close to those, you just take the documents that are close to that question, and that gives you the ability to control how much you put into the prompt. So you could select, for example, only the 2 most relevant articles about the question. You put them into the prompt, and then you answer the question. Okay, so this is the approach. It's called retrieval augmented generation, and it's the approach that everyone is using nowadays for this. And now what you were asking, I guess is, what's the difference between doing this or doing fine tuning and so on? In my mind, the problem about this is that the quality of the embedding matters a lot. So if your embedding quality is not as good, usually you cannot use the same model like GPT-4 to calculate embeddings. So the quality is going to suffer a little bit. And maybe you don't get exactly the relevant articles. So that's not ideal. But to be honest, it's the best solution we have right now. Because about fine tuning, I think the only thing that would make sense right now is if you want to fine tune a very small model. Okay. So as we mentioned before, like if you want to fine tune it on a specific task, yeah. But fine tuning on just a corpus of text, it's something I've tried, but it doesn't seem to help a whole lot. And it seems to, for what I'm reading, it's very, basically everyone's finding the same. It's like, if you have a specific task like summarization, you can teach it to do it, but you cannot just give it, the Bible and then expect, everything, to be knowledgeable about the Bible. It doesn't work exactly like that. So in this case, I think retrieval augmented generation is the best chance you have. And in general, everything you can put in the prompt, it's going to work much better, because as we've discussed earlier, these models learn such general functions and algorithms that they can use on the prompt, that basically you get all that for free. So if you can put it in the prompt.
You killed my startup idea with the Bible, actually. I was going to fine tune one of the open source models, because I know people have questions about the Bible. So just create an app. So you just killed my dream.
So I think it makes sense when what you're trying to do is change the style of the language, but not about the content itself. It's kind of, yeah. But yeah, there's a lot of research on this area as well. People trying different things and what works better. To be honest, it's a bit of a race against the clock, because what's happening more and more is that context lengths are getting bigger and bigger. So this tends to matter less and less. And now we have like 100K context lengths, and there's techniques called rope, for example, to make them even larger and so on. So maybe in like 2 years, we won't be talking about context lengths anymore, and then none of that will matter. So
yeah, I was going to ask about content length and attention, because right now you're telling me that GPT-4 cannot be my therapist. It cannot remember all our conversations, so it can be my therapist even from my childhood traumas. Even if I've been trying that, but that will not work.
Exactly. I mean, there's techniques to go about that. So you can use embeddings. You can use a technique that I've been trying recently, is trying to use knowledge graphs. So trying to have the language model compress information into what's called triples, knowledge triples, which is subject, relation, object. And then basically put these into a knowledge graph. And then whenever you mention something in your therapy session, the model would recall anything that is relevant to those things. So maybe you're talking about, your family or something, no? And then I pull out everything I know about your family, and then that's part of the context now. And I can answer with things that maybe you've told me 3 weeks ago, right? So this could be something that could feel a little bit more human, but I don't think, I mean, we have to try it, obviously, and we have to work with what we have. But hopefully in the future, you can literally cram your entire, all your emails, all your texts, everything into one context, and then just have a great therapist that knows everything about you, right?
Yeah, I mean, I think that's the future, actually. Yeah, it's the movie Her. But
Yeah.
tell me more about how you're building this graph.
Okay, so it's basically in the same way that you would connect this embedding store in the retrieval augmented generation example that we mentioned. You connect a graph database, and basically you put in the loop, basically when a user asks a question, you have this extra step of recalling, hey, let's see what knowledge I know about these things that you're talking about. You say about log out. Okay, let's look at everything I know about accounts or account management. And then there will be some triples that say accounts can be deleted, accounts, you can log out of accounts doing whatever or something like that, right? In this case, it's not very useful because it's how can I do this? But for example, if in a conversation you're mentioning a company and there's triples about that company, like this company has that many employees and it produces something else, then you already know what you're talking about. You don't have to explain again about that company what it is. So yeah, and potentially you could do that even in a customer support setting. You could use that to store triples of information about your customer. So for example, customer purchased this on this date, and then in the same order they purchased this and that, for example, and you pull out all this information when a customer asks, hey, my recent purchase, I want to refund, I want to refund, and then you like kind of pull everything together that's relevant. Yeah.
So basically, you could already do that now in a company with your CRM. You could map that out in a graph database and then
Exactly.
use your large language model to query and to make predictions or whatever you want to do.
Exactly. And the cool thing with the better language models is that they are able to decide what the query should be themselves, which is kind of an extra step. So a customer might ask about, hey, I want a refund of my last order. And then a language model will think, what query should I do to get the information that I need, right? And maybe the query is, get me the orders made, before that date, and then do this and then do that. And the language model decides what to do, almost like an agent, right? So I think this kind of micro intelligence that you can kind of infuse in every part of the process is something that is still not completely explored. And, it's kind of not so obvious, but it's really powerful, I think.
Maybe going back more to the intuition of it, like you've mentioned as well before, something that I didn't know, that with the prediction of movements of a robotic arm that LLMs can do, how are they so good at problem solving? Like, what do you think? What's going on?
It must be that they've been fed so much data, basically. So there's an intuition that I think is really simple for everyone to understand, which is, so language model, like neural networks, they have a capacity. So they have a number of parameters. And in a way, you can imagine as a person having a capacity, right? You have a brain and you have a specific amount of energy that you have to spend, right? And then if I give you a task, like, I'll give you these 3 numbers and you have to tell me these 3 numbers in an hour. Okay. So you'll take the thing and you'll get really bored. You'll memorize them over and over and over again. And then you will go have a beer. And then after 1 hour, you will tell me the 3 numbers because you've already memorized them. It's so easy, right?
If it's just one beer, maybe, but if it's a few more.
So that's because the data is so little that you have enough capacity to memorize it and think about something else and write a poem at the same time. But if I give you like a book to read, then it's not that you cannot memorize the book. You have to understand it. And what we do is we read it kind of diagonally. We try to get the gist of it, and we try to basically compress the information in a way that we can access it in an hour. And this is actually a theory that a lot of people have, that in a way they define intelligence as compression. So how intelligent something is how much it can compress information. Okay, that's, I think, an interesting perspective. In a way, what we do when we read a book is we compress information, and then we try to figure out how to create a model that's very, very general, so that we can answer questions about the book, for example, later, right? And if your capacity is big, but also the data you have to learn is really big as well, you cannot memorize it. So you are forced to create these models and these abstractions in these hierarchical representations and these algorithms. So I suspect this is what's going on with large language models, that they are forced to learn more general relations and concepts about the world and algorithms and things like that, because if they didn't, they couldn't be as good basically as predicting the next word in so many different domains, so many different pages of the Wikipedia, right? If you think about it, they know the entire Wikipedia. Like, they know how to predict it. That means they know a lot of things about our world, right? And
Isn't that amazing? Like, this is one of the things that I always keeps me amazed. And I'm just imagining the potential if at some point in time in our lifetimes we can actually use Neuralink to connect to that, and we basically get all the knowledge all the time of everything that has been written. Like,
I don't think that's that far off. I'll tell you why. So, something that really surprised me is a result from a group. I forget where they are, but they were using stable diffusion. So, stable diffusion is a latent diffusion model. Okay, so it takes a text and then it projects it into kind of some kind of embedding, really, and then it produces an image. Okay, that embedding space that it's basically tries to, because it's been trained with so many images, it has a lot of concepts, animals and plants and backgrounds and colors and all this stuff. And they took, basically they made a model that would connect to your brain, basically, and when you see a picture, it would encode it into the embedding space of stable diffusion. And the results were amazing. You've seen the results, I guess.
Yeah.
I mean, you see a teddy bear, and Stable Diffusion produces a very similar teddy bear with very similar colors and everything. So in a way, they created a model that maps our embedding space, how we encode images, into how Stable Diffusion decodes images. So knowing this, I mean, it's not
scary. It's scary, first of all,
it's scary,
because now your dreams are not only your dreams anymore; they can be anyone's dream.
Exactly. I mean, for me, I don't know how to draw. So for me, I don't know, you don't know how much I would value something that could just read my mind and produce an image. Like, that would be amazing, because for those of us who don't know how to draw, for me, it's magic when someone is drawing something out of memory or out of their imagination. It's amazing. How can they do that? Maybe we can do that soon with Stable Diffusion. But yeah, it wouldn't be completely outrageous to think that we would be able to map maybe the other way around. So a concept in Wikipedia into an embedding that is, understood by a language model, and somehow translate it to our own intuition of those concepts. So suddenly you would get these kind of flashes of like ideas, that's pretty crazy.
Yeah, for me, I mean, the crazy part is already the fact that we have all the knowledge in the world, that it's in a brain that we can talk to, and that it has basically all the information we've ever had and can answer questions. So basically, information is no longer a problem for anyone. Like, I was thinking, like, even with this thing that I'm doing with the podcast and personal branding and so on, what information can I give people that they do not already have, and for free? Like, everything is free and it's available. So in this world, in this reality, what's the value of humans? Like, I'm starting to ask myself, like, what are we good for? Because we thought, I mean, sure, there are different ways of knowing, but we live in the tyranny of propositional knowing, which is basically we talk about words, beliefs, and ideas. And there's a machine now that we've programmed with all our knowledge that has all the knowledge in the world. So what are we? Maybe we need to start asking better questions to ourselves and to the machine, and try to see what do we get from there.
Yeah. And so far, what I think hasn't been solved is what we bring to the table is we want something. We have goals and we want things. And large language models, they don't want anything. And they cannot want
anything. Is this due to our biology, and can that change?
I think it can change, because as soon as you see reinforcement learning agents, they learn to want things and to value objectives and to plan, right? This is, I think, what's missing in the equation, because it's something that we bring to them. We say what we want to do, and then large language models help us to get there. But maybe in the future, we don't even have to explain what we want to do. We just kind of give a goal, like, I want food on the table every day. Figure it out,
But for example, like, and I wanted to ask you about AutoGPT as well, because it's already more of an agent. But if you have two agents, can you ask one agent, like, set the goals for the other one, and the other one just executing? So can that become kind of a self-generating goal machine?
I think so. I think they've explored exactly that, like kind of different roles, like, a director and a planner and a worker and all this stuff, no, and kind of these things. I think that can work. It's still very primitive, but I'm sure it can work. For sure.
Okay.
I think the value of human beings, though, like, I think the most surprising thing that we've learned in the past few years is that we are actually creative. I think we can go out of distribution, what's called out of distribution, in a way, but in other ways, I think it's really hard for us to do so. So sometimes, and some people will do it, and will have this crazy idea that is completely outrageous. But most of us, we kind of work within the same distribution all the time, and we are not. It's not easy for us to come up with very new ideas. And for me, the AlphaGo example, I don't know if you saw the documentary, but I was following when it was going on, the match, and also at the documentary. And there was this move, I think it was called the move 37 or something like that. And it was a move that AlphaGo made against Lee Sedol, which was the world champion. He made this move and everyone was frozen. They said, this move is impossible. Like, no human would have thought of this. It's so out there, completely out there. And it was a move that it turned out to be decisive to win the game, like later on. But it was a move that was just not human. So in a way, I would think that creativity is actually, so in maybe in the future, the captchas of the future will actually check for lack of creativity. So like a human response will be the most boring one, because machines are able to go so out there.
But
I
we
don't
we
know.
haven't seen that with LLMs, right? Because at the end, if LLMs are prediction machines, prediction based on what has already been said, and even if it's combined in a way that we might not have combined before, but they are not creative at the end of the day. They are just prediction based on combination on what they have learned from us.
That is a way to see it. But if we follow the thread that we were talking before, that they can learn general functions and general algorithms, and they have the language, why cannot they produce something truly creative? I think they could. I think it's possible, or theoretically possible, that they can produce something truly creative, even though they're kind of very forced into not doing that, because they kind of, when you sample tokens from that, you go from a distribution and you sample the most likely tokens. But if you go with a very high temperature, I don't know if you've ever played with temperature in these models. The intuition behind temperature is how crazy you want them to get, basically. So if you go really high with temperature, I think you can go into spaces of the token spaces that are completely out there. I don't know.
Okay, maybe not off topic, but stepping back into intelligence and consciousness. The other day, I was talking with a friend, and he was saying like, "Yeah, these machines are not intelligent." I wrote it. I read it in an article, a contrarian article saying that yes, the LLMs are not intelligent. I disagree, but I wanted to get your view because I think they are intelligent. I think intelligence is a capacity to solve problems, and from what we've seen, they really solve problems that most humans would have issues solving. But maybe on the consciousness, you mentioned like you believe there might be well, there's still at least the open question, and we need to define better what is consciousness. But I don't know. What are your thoughts on these two, on intelligence and consciousness of LLMs?
So first, about intelligence, I think it's such a loaded word, right? Like, I think intelligence is completely is the same kind of word as fitness. So fitness really has no meaning without environment, right? So something is fit in an environment, and it's not fit in another one, right? So in a way, intelligence, I think, is the same. Intelligence is something you can see and you can really acknowledge that it exists in a specific environment where there's problems that you have to solve, and maybe you see someone who is very gifted at solving some problems that you want to solve and you cannot. Then you see, oh, that person is really intelligent. And it's like, wow, that's great, right? But for example, in a different environment, like the jungle, for example, LLMs are useless, completely useless. They're not even embodied, right? They cannot make fire, they cannot find food, they cannot do anything like that, right? So I think intelligence is highly contextual. And even there's forms of intelligence, everyday intelligence, that LLMs are very far away from achieving, or even any kind of neural network or artificial intelligence, like, for example, cooking or folding clothes. Like, there's no robot that folds clothes in any home, any kind of clothes, right?
But isn't this, and maybe I'm just opening an opportunity here. And I learned that in industrial design. A lot of times we design machines that replicate how we humans do things. But then when we get to really solve the problem, it's when we reinvent the process in a way that only machines can do and humans couldn't. Maybe through LLMs or other models, we can start designing those machines that fold clothes in a way that humans don't, and it's much more effective, and that basically they can do it hundreds of times faster, more efficiently, and then they get better at that.
I believe this is possible. That artificial intelligence can help us design things that eventually, can bring intelligence in that way, no, in designing things that we haven't thought of. Maybe not LLMs, although I will eat my words for sure in the future because LLMs have kept surprising me every time. Okay, but I could definitely imagine like a goal-oriented agent, some kind of goal-oriented agent, being able to explore the design space, because in the end, design or industrial design or any kind of design is exploring a space and finding the solution that fulfills a specific criteria and is efficient and is easy to produce, and so on. And this is also already happening with protein folding, right? Like the AI that solved the protein folding problem, and with drug discovery and all this stuff. So I don't see why not, really. So in the end, we will have like true superhuman intelligence in every domain. I don't think that's impossible, even though some people they dismiss that idea. They say they can never be as intelligent as us with everything. But
Maybe going back to the protein folding question, is it done through LLMs?
I don't think so. I read about it a while ago, and I don't think it's LMs, but for sure there's some kind of transformer involved, because, like, time and time again, transformers have been applied to literally everything. Um, an example that really surprised me, that was back in the day, also by DeepMind, so that's why I'm not surprised that they are using transformers, because they are in love with them, was when they talked about Alpha Star, their basically game playing AI that plays
Mhm.
StarCraft 2, which is a game that I really enjoy. So that's why I was really into that model. And the idea is that it played the game, but the state space of the game is so huge compared to other games that it was really hard. It's really hard to learn with pure reinforcement learning, which is a technique that everyone was using back then. So it was not working, basically. And the lead of the project, Uriol Viñals, who is like a massive figure in the scene nowadays, he had a background in sequence modeling and transformers and language. So he decided to apply to see a game as a sequence of states, and you only have to decide what the next state is. So what actions to take in the next state, right? It's a pretty weird idea. It's not a sequence of words, but a sequence of states of the world, right? And applying that notion, basically, it made it work. And from then, transformers have been applied to modeling any kind of sequence, like sequence of anything. So yeah, I wouldn't be surprised if AlphaFold works like that.
Yeah, because I think that applying it to states, a sequence of states, it makes much more sense than continue to trying to go with everything through LLMs. Because at the end, LLMs have been trained on human language, and human
Human words, yeah.
language it's limited in expression of ideas. Like, let's remember why human language was invented, or why we invented it, and it's basically to collaborate between one another, to get food, to negotiate, and things like of that end. It was not created to find truth or to help us understand how the universe works, really. Like, we've used it for that, we've adapted it for that. So maybe using human language, it's not the way, but maybe trying to map out states of reality and trying to predict the next stage, it's a better approach.
Yeah. So the general technology of transformers and sequence modeling, I think, is much more promising than LLMs, even though, as we've seen, LLMs can learn arbitrary sequences apparently now. What I have a hope for, actually, is that I don't know if you've ever tried GPT-4 to ask a question to GPT-4 about something complicated that you don't understand, and then you ask it to explain it to you like you're 10.
Yeah,
And it's masterful. Like
it is
the
amazing.
education side of things, like it's one of the best educators I've ever met, GPT-4. And I believe that even in the future, when maybe AIs are running around discovering new things about the universe, they might be able to explain them to us very simply, which is something that I would have not expected. I would have expected that, super intelligence would just go off on their own and we would never be able to catch up and we will never understand the new things they build, right? But maybe they are
Yeah,
able to explain it to us.
I actually, one of the more appealing things I would say I see in these models, or what could really transform, it's on education. Actually, they can really transform our society. And I was listening to another podcast related to can we apply, or how the great minds of the past have become the great minds that they have been. And this is basically based on the tutors that they had. And basically now anyone can have a tutor such as like Einstein or anyone like that, and to bring their knowledge at the level you're at and continue growing. So I think the applications that you can get from these models in regards to education, I think they can be transformative if we know how to ask the right questions and how to really use them properly.
Absolutely. That's something that will take some time to actually for people to realize, especially people in education, because when a tool, I mean, right now the tool is a bit disruptive. Like the ways in which we evaluate people are outdated, and GPT-4 and ChatGPT are basically destroying those evaluations, and then the whole educational system is on fire, basically, thanks to ChatGPT.
It's not adapted to our current reality. Like it's not adapted to knowledge. It's a commodity that basically you get with your at your fingertips just by asking a chatbot, basically.
There's something I wanted to mention. Actually, about education, I've been playing with an idea of using it for using GPT-4 for language learning. So this is one of my passions, learning languages, and I found I was completely astonished at how good a tutor it can be. If you prompt it properly, it can be the best tutor you've ever had, because it's a unique tutor that first has infinite patience. So it will never get tired of like, oh, it will never get tired of like follow-up questions and like, going deep into one thing, rabbit hole, and going back, and also the GPT-4 can literally use only the words that you already know, plus a few more words of that level, which is a skill that I don't think many tutors can have. Really modulate your language to the point that your student understands 70% of what you're saying exactly. That's wow, that's amazing. I think that they're super promising.
Yeah, talking about one of the other promising applications that it's already being used quite a lot, but some people seem to be afraid of it, and it's Copilot in development. Can you tell me more about first your experience with Copilot, or any other, or even if you're doing it with GPT directly? And what do you think? Where do you think this is going? What's the role of a software engineer in 1, 2, 3 years?
I think I cannot live without AI right now, working as a software engineer. So I started using Copilot a few years ago, and it saved me, at the beginning, it saved me hours every week, literally hours, because a lot of the work we do is basically deciding what to do. And that might be the hard part. But then the tedious part is then doing it. Like you already know what you need to do, and then you have to do it now. So that's kind of like, okay, and writing tests, for example, is an example. You already know the tests you want to write, and they are very repetitive and tedious. And in the worst case scenario, some people might choose not to write the tests. I'm not talking for myself. It might have happened, might have not happened. I don't know. But
I've seen
it's
it
hard.
more often than I would want to see it.
So yeah, basically, there's a lot of tedious automatable part in software engineering, and I find that Copilot helped me a lot in that regard. But recently, I've been using this editor called Cursor, which is a fork of VS Code, Visual Studio Code. And you can use it for free, basically, if you have an OpenAI API key. It connects directly to GPT-4 and GPT 3.5. And it's very tightly integrated in the editor. And what I find is, I mean, before I was just copying and pasting things from GPT-4 and like helping me write tests, for example, for a class and things like that. But now it's so tightly integrated in the editor that the feedback loop is very fast. And I think, I mean, it's made me many times more productive, many times. I don't think software engineering will disappear, but it's similar, I think, the analogy to when people were writing assembly code by hand. They knew the ins and outs of CPUs, and they were very specialized on specific hardware, and they were really good at it. And then C came along. And then these people were like naysayers. It's like, C is just stupid. Like, who would like to write this high level code that's just slow and it can never be as optimal as what I write? This is useless. No one's going to use it ever. Right. And, fast forward a few years, everyone is writing C, and very few people are writing assembly. And I think it's a very similar situation, also with higher level languages like Python and Ruby. The things that software engineers need to do is to learn to use this new tool and basically let go of some of the tasks that now, compilers are doing, right? Maybe now Copilot is doing some things like writing specs, writing tests for your code. And there's some things that it's going to be hard for programmers to let go. Like, hey, but I really enjoy writing this by hand. But everyone's going to be like, yeah, but there's no point. GPT-4 can do it for you. You dedicate yourself to something else, to something harder, or to at least the higher level picture of what you were trying to build, right? It's going to be a shift for sure, especially because there's things that we enjoy doing that now are just going to be not cost efficient to do by hand. And that's a bit hard. I think that's going to happen to a lot of the knowledge workers, because there's a lot of things that you enjoy doing, but there's no point. You cannot justify doing it by hand if GPT-4 can do it for you, right?
Yeah, there's an example, for example, for product managers that it's also writing documentation, product documentation. Yeah, GPT can do it much, much better. But then you will have on the other end someone summarizing that documentation with GPT as well.
Yeah.
That's
Which
I
is-
got
yeah.
I got a question the other day from a friend that he wanted to do a software bootcamp a few years ago. He didn't, and then he was asking me again, should I do it now? And a few years ago I said, just do it. It's the best investment you're going to do. And if you like, I mean, he studied a little bit of programming in university, but then he went and did journalism. But then he was thinking back, hey, maybe I should get into that because I really enjoyed it. And I said, yes, do it. He didn't. He's asking me again. I didn't have the same answer now, but I said like you should potentially, and I don't know if there are such kind of bootcamps right now, but a bootcamp that is focused on making you become a junior mid developer leveraging GPT. Do you think, or what would be your recommendation? Maybe let's step back for someone who's getting into software development today, knowing the environment that we have with all these large language models and Copilot and so on. What would you recommend to someone if they want to get started?
What I'd recommend someone is to first get ChatGPT Plus and use GPT-4. Have a tab open with GPT-4 the whole day and just keep talking to it. Okay? And then learn whatever you need to learn. You want to learn Python, data science, Ruby, React, anything. But you can learn much faster thanks to GPT-4. And I still think there's value in not only learning to program, because in a way, learning a language is what people are afraid that it's going to be useless. It's like, oh, now I'm going to write Python and maybe Python is written by GPT-4 in the future. I think when you learn to program, the language is kind of a byproduct of what you learn. You learn a language and a set of frameworks and libraries, but you're learning to think like a programmer and build things. And this transfers way beyond that. So that's why I always say that it doesn't matter too much what you learn at the beginning, as long as it's not C++. Don't go there first, because you'll get discouraged. But as long as you learn something, I think it will help you. It will make you more competent at building things, including building things with AI. So I think software developers, we still need new software developers, and we need new software developers that know how to work with AI and that they have a tab open with GPT-4 the whole time and they work with the AI continuously, because those are the people who are not going to be replaced. So in a way, they say, it's not the lawyers are going to be replaced. Lawyers without AI are going to be replaced by lawyers with AI, right? It's like any tool. So the same with software developers. It's like software developers with better tools are going to replace software developers without those tools. And even not all of them, of course. There's niches that obviously there's still going to be, people writing assembly until the end of time. But yeah. So I would recommend people to still do bootcamps, still to learn this, but use GPT-4 from the beginning.
Okay. Now, again, question about the future of the next 3-5 years. What will a software engineer be doing in 3 to 5 years? The same, or do you think this will have
not at
changed?
all. Probably none of the stuff that I'm doing nowadays will be what we do. So
what can you imagine, if you can?
I'm basically thinking of feedback loops that are insanely fast. Like we have a product idea, and then we literally talk to GPT-4 and we have a pull request, in the code base after 10 minutes. And then we launch it under a feature flag. And then we iterate and then we tweak, but we're talking very, very fast. And when there's a bug, you jump in there and you have a lot of context given to you by GPT-4. This is what happened. The user did this before, and the bug is probably there. Have a look.
Hmm.
Okay, maybe yes. Boom. Do you want me to auto fix it? Yes. This kind of next level feedback loop, which I think is amazing.
Yeah, that raises a couple of questions. First, is there any big revolutionary improvement in DevOps with LLMs? And then the second one on the monitoring tools. Are they already using that? And have you had great experiences that have changed because of these new tools?
What monitoring tools? What do you mean?
Yeah, kind of the DataLogos, the New
Hmm.
Relics, and so on and so forth.
It's a good question if any of this will change. I mean, still, I would believe a lot more will be about having these monitoring tools, because the number one problem that will be with LLMs is, in the end, is trust. It's like, do you trust that the code that was produced by the SPR is okay, that everything is going fine? And the trust will be something that you need to trust it somehow, but you need monitoring. You need to know that customers are still making purchases and everything is going fine, right? So monitoring is going to be important in that regard. About DevOps, I'm not sure how much it can change, because it's already very automated in a way. Like, there's a lot of these kind of languages to spin up entire clusters of things and spin them down and stuff. So I'm not sure how much this will change, but yeah.
Okay, let's start wrapping this up a little bit. But before going into the more philosophical realm, I wanted to ask you if there are any other industries that you believe will be highly impacted in the upcoming months and years with LLMs that haven't yet reached those industries, but that you think it's coming.
I think everything that is knowledge work, which is a lot of industries, and especially us living in cities, like, we will be surprised basically how much work is impacted by LLMs. And in a way, I hope this transition is very short and that we can start working on automating and helping the jobs that are actually, that people don't want to do, right? Like the hard jobs that are dangerous. These jobs should be automated pretty soon, because if we just automate the jobs that we enjoy doing, it's kind of a waste. No.
Yeah, that's what we're doing now. But actually, like, to automate these difficult jobs, you actually need people who have a lot of skills to generate the new technologies to automate that, because it's not that easy. Like, let's go back to the kitchen and cooking. Creating a robot, basically, that because you need mechanical components that move and create food. Basically, you cannot just do it an amazing recipe with an LLM. You need a diverse set of skills, and you can do that with a team, multiple teams. But I don't know, I think that the coordination layer of all those skills to actually deliver that, it's where it gets so complex that I don't know how much progress are we going to be making in the following years. And the same happens with the rest of more manual work.
I think it probably looks similar to any changes in agriculture over the hundreds of years that agriculture has been getting better. It's simply that one farmer can now feed 100 people, 1,000 people, 500,000 people, right? And in the same way, a chef now can serve 1,000 people a night. And before it was 200, because it has a bunch
Mhm.
of robots and it has a bunch of things that are automated. In a way, I think that's how it looks, which I think is very promising, especially for things that are currently very limited by how many skilled people we have. So, for example, medicine and healthcare is one of these, right? So we have a huge bottleneck on, for example, primary healthcare. Like, if everyone wanted to go to the doctor every week just to check in, nothing would work. Like, literally nothing would work, right? But it should be. You should expect people to check in every few months, and maybe check on changes in the diet, exercise. Maybe something, and that would be amazing to have a primary healthcare that you could talk to every few months, right? And that's not possible right now. So for like early diagnosis and things like that, I think these kind of automated or LLM or AI based doctors, I think they are very promising, because you could talk to them as often as you want, and they would basically direct you to a specialist later on if you have a problem or not, right? But yeah, then you would have content, because right now there's just not enough skilled people.
Yeah, we need your knowledge graph connected to GPT for that to get all the history of the patient.
Exactly.
And how do you keep growing in AI? How do you keep updating yourself, your knowledge? Like, what resources do you recommend for that?
So there's this webpage called Papers with Code. This is amazing. Okay, amazing. Bunch of papers are there. They have code, which is not a given. A lot of papers are like, we did this, and you have to trust us. But a lot of them have code, and it's great. And then the classic, podcasts are a big one for me. I love
Which ones?
following.
Any
So
recommended?
Lex Friedman, obviously these, but basically sometimes I look for the interviewees. So for example, I would look for Jan LeCun interviews, right? And it's like wherever they appeared, I want to hear what they said, right? And people from the community like Jan LeCun and Oriol Viñals, these kind of people, whenever they have something to say, I want to hear it, basically. And that's what I try to keep up with.
Okay, now let's really jump into another realm of questioning. But for you, what gives you happiness and fulfillment? Because we've been talking about AI, and you said you're really excited about that. But is that your life, or do you have any other areas where you think
That's a big driver. So I would say there's things that bring me happiness, and AI is not one of them. So AI brings me, basically it's what drives me. So it keeps me going to the next thing and the next thing, and kind of finding out and building, and kind of it's the excitement, right? And then what brings me happiness and keeps me grounded is completely different things. So for example, music. So making music is something that it's very highly correlated with when I'm making music, I'm happy and content and grounded. And when I'm not making music, I'm like off balance. You know what I mean? So I guess any kind of creative endeavor, like for some people will be writing, and for me it's making music. These kind of things really make me happy. So when I explore kind of the creative space of something I enjoy, really keeps me happy. And obviously exercise and a balanced lifestyle, I think this is really important. It's something that I've learned maybe too late, but to be honest, it's never too late. But it's important to have balance, because personalities like me, I tend to be very intense, and when I get driven by something, I don't want to stop, and I don't know when to stop. And many times that can lead to burnout, and very easily can lead to burnout and lots of problems. Aside from health problems, obviously, from being sedentary and working with computers. So you need to really find balance and stop working and save your energy for the next day and spend your energy somewhere else, like cooking, doing exercise, meditation, whatever it is. And this keeps you going for much longer. This helps you think more clearly and just make better decisions. So I think it's worth it. And I wish more of my colleagues in the industry would kind of pay attention to this, because a lot of them are consumed by what they love, which is understandable. I understand it, but it's not sustainable.
But how do you manage that? Because for me, I have the same, and for me, this is an addictive personality, basically. Like when you get motivated by something, your curiosity spark, like, I just don't want to stop. I just want to be doing that for now. And then maybe I get bored and then I jump to another thing. But it's very difficult to stop when you're actually doing that. How do you do that? Do you have a routine or something?
I have kind of hard rules in a way. Like, for example, pretty much I would say no matter what's going on, around 7 p.m., it's time to, I cannot code anymore. I cannot do anything that is remotely creative that is not making music. So making music, I can make it whenever I want. So that's kind of the rules. And same with studying languages, whenever I feel like. But things that I really, really don't know how to stop when I really get into them, they have a hard rule, like a hard cutoff. 7 p.m. gone. I cannot do anything. And if I want to do something, I can keep thinking about it. I can go for a walk and keep thinking about it, but I'm not allowed to go on the computer, because otherwise it's just gonna destroy my sleep. And then next day will be, it's just how it works, I guess.
Yeah, I know. And having a kid and trying to have a side hustle and everything, yeah, I definitely know how it works. And maybe the question of questions, is there a meaning of life, and what's the meaning of life if there is?
I found over the years, probably the same happened to you, but growing up, I tended to think that everyone is like me. So everyone wants the same things that I want. Basically, that's what kids grow up thinking, I guess, because that's a natural thing to think. And it's been a very hard lesson to learn that people want different things, and that people are happy with different things that have nothing to do with what you understand as happiness. And that really confused me. So basically, it left me thinking, okay, first stop prescribing to people what they should do, because that's something I tended to do a
That's
lot. And
hard,
like
man. That's
sometimes I
really
do
hard.
it,
I know what everybody needs. Let me tell them.
Exactly. So basically, kind of let them do what their thing, and focus on your thing and what makes you happy, and just go with that. And for me, it's about creation and discovery. So it's, I need to keep creating things and discovering what's in the next corner, and the next mountain, and behind the next tree. I need to keep going like that, and it's a never-ending pursuit. So it never ends, and there's no enlightenment at the end. It's basically you just keep going, and that's it. That's for me, at least.
And if you wouldn't be doing what you're doing now with your life, what would you be doing?
If I wouldn't be what I'm doing, so you mean like programming and computers and all this stuff? That's a really hard
And
question.
stuff, yes, computer and stuff.
Computers and stuff. I think probably I would probably be really seriously into cooking. Something I didn't quite get into seriously, but I think I could, because I've had periods where I've been very intense about cooking. And in general, anything really that involves creating. So it could be also creating businesses, like just finding a problem and solving it, by creating a business. It could be about planting mushrooms, and selling supplements, or like cooking dishes and having a pop-up restaurant or whatever, something like that. I think I would enjoy, as long as it's creating and sharing with people. Yeah.
Who knows? I yeah, I haven't watched Arnold Schwarzenegger's documentary, but apparently he had three phases of his life. As you might know, one as a Mr. Olympia, and then he went into acting, and then he became a politician. Maybe you
Yeah.
have another 2 chapters ahead.
Very different ones.
All right, man. To close this up, is there anything that we didn't discuss that you believe we should have talked?
I think that's pretty much it. I think we talked about so many things, completely, out of order. Hopefully, the listeners will be able to piece everything together. But yeah, I've enjoyed a lot, and
Awesome.
it's a topic that I love, basically.
Yeah, me too, actually. I really love it. And it's good when I have the chance to speak with people that know much, much more than I do. Because I always learn things, and I always have the chance to ask for things that I think I know, or I kind of have an intuition, but then I get the details, which is amazing. So I really loved it. Yeah. And if anyone wants to reach out to you, or if you want to be reached, what's the best way to do it? Maybe you can also say like, yeah, I'd rather not be bothered by anyone, but
No, I love talking to people, and I actually sometimes as a hobby helping them with ideas they have, or like bouncing ideas. I love that. I love anything that is kind of creative. So sure. I mean, I don't have social media, but I do have a blog/website. I'm on LinkedIn. That's the only social media I am. That's really sad. But yeah.
like all the grown-ups, man. All the
Yeah,
grown-ups.
exactly. Like a serious professional.
Exactly.
So yeah, I have a blog at txus.github.io. It's one of the GitHub pages one. I can send you a link later.
Nice.
And there I try to write about AI and things like that. And that's it.
Awesome. Yeah, send me the links. I'll post them when I post this. And yeah, it's been amazing, man. Thank you very, very much for your time.
Cool. Thank you a lot.